Hello everyone, in this video we are going to see about the asymptotic notation. This asymptotic notation is a mathematical tool which helps to find out the behavior of an algorithm, which is the limiting behavior. So they are also called as an asymptotics, which is a method of describing the limiting behavior of an algorithm. It is a tool. Asymptotic notations are the mathematical tools to represent the time complexity of algorithms for the asymptotic analysis. So here the term asymptotic defines the limiting behavior of the algorithm. Asymptotic notation is used to describe the running time of an algorithm. So how much time the algorithm takes to execute, that is the running time of an algorithm, and based upon how much input is given. So this running time depends upon the size of the input, which is n. There are three different notations, namely big O, big theta and big omega. These notations are called the asymptotic notations that describe the behavior of an algorithm. Here big O notation, shortly called big O, it specifies the worst case scenario. That means what is the maximum time the algorithm takes to find the solution. And omega notation, shortly called omega, this specifies the best case scenario of an algorithm. And the theta notation, this represents the average complexity of an algorithm. So the complexity all depend upon how much data is being used in the process. Let us see one by one. First is the big O notation. It specifies the worst case scenario. It represents the upper bound running time complexity of an algorithm. So what is the maximum time the algorithm takes to execute the process? That is the upper bound running time of the algorithm. So this worst case defines the maximum time required to complete the program execution. Mathematically, this is defined as big O of f of n is equal to set of all such that g of n there exists c greater than 0 and no such that f of n less than or equal to c g of n for all n greater than n. Actually this is the number of the greater than the n of O. So actually here this mathematical definition says that there exists no such values which is less than or equal to, which means it is always the maximum time. So c is the constant over here. Let's take a few examples to understand how to represent the time and the space complexity using the big O notation. Big O notation, the first one is O of n, order of n, which is only the one element we are having. It represents the complexity of an algorithm that always execute in the same time or the space regardless of the input data. How much data there may be or how much data there or how much space is there, it always takes a uniform time. That is called as then they always execute in the same time. That is the one example of big O notation. The value is order of 1. Example is accessing an array index int num is equal to array of 5. Actually this is one example where we are find the location of the element array of 5. We are going to access the fifth element of the array called ARR and we are going to store that value in the variable num. This is one memory access. So this takes big O of 1 as the time complexity. Let us see the next example using the big O notation of n size. This O of n represents the complexity of algorithm whose performance will grow linearly in direct proportion to the size of the input data. So when the size of the data is 100, it always have the 100 is the complexity, that is the order of n. Okay, so that is the maximum one. This is the worst case scenario. So the complexity of the algorithm grows linearly, that is in direct proportion with the size of the input data. Let us see an example here. The execution time will depend upon the size of the array. When the size of the array increases, the execution time will also increases in the same proportion linearly. So the example is traversing an array. That means visiting each element of array is the traversing. So if there are n elements in the array, it will take n as the time complexity, that is the linear proportion, which is the example for traversing an one-dimensional array. Now we'll see the next example using the big O notation of order of n square. Big O notation of order of n square represents the complexity of the algorithm whose performance is directly proportional to the square of the size of the input data. So suppose the input data value is 3 and its square is 9. So now this big O notation represents 9 is the complexity of the algorithm, that is the directly proportional to the square of the size of the input data. So example is traversing a two-dimensional array. For example, an array of dimension 3 by 4, 3 rows and 4 columns. In this scenario, this worst case, which is the big O notation, will take 3 into 4 as the 12 as the size of the complexity of the algorithm. That means if the n is same, for example n is 5, means 5 into 5 is 5 square. If there is an unit matrix of 6 dimension, then the traversing time will be 6 into 6. So the order is n square. So this is one complexity, time complexity, where the complexity of the algorithm is directly proportional to the square of the size of n. So here the example is traversing a 2D array. Here suppose an array is size of 10, okay, and it is of 2-dimensional. It has to traverse or visit all the 100 elements, 10 into 10. So here 1 of 1, 1 of 2, etc. up to 1 of 10. That is the first row. Then 2 of 1 to 2 of 10. Then 3 of 1 to 3 of 10. Similarly, 10 of 1 to 10 of 10. So this traversing all the elements of the array will have 100 as the time complexity, which is n square, 10 square. There are also some other big O notations such as logarithmic growth, order of log of n, log linear growth, order of n into log n, and then exponential growth, order of 2 power n, and factorial growth, order of n factorial. So based upon the number of inputs, the time complexity varies. So all the time complexities of different cases are given as a graph here. The input data, the x-axis shows the input data and the y-axis shows the complexity of the algorithm. Here, as a minimum, O of 1 is the case where there are element is only 1, the size of the array is 1, or the element to be accessed is 1 element, and log of n is also of the same complexity. And then we are seeing the next case, which is the order of n complexity, and here this is the order of n into log n complexity, and order of n square, order of 2 power n, and order of n factorial. So this mathematically you can say that O of 1, which is has the least time of the comparison or execution of any process, and this order of n factorial, which is the highest time complexity. So these are all the different cases in the big O notation itself, where the complexity of the program based upon the size of the input data n. So next is the omega notation. This omega notation always describes the best case scenario. So what is the best case is, it always represents the lower bound running time complexity of an algorithm. That means at the minimum time how the program can execute and show the result. So if you represent the complexity of an algorithm in omega notation, it means that the algorithm cannot be completed in less than time than this. That means it always defines the least bound of the timings. So that's what given at the mathematical this notation. This omega of f of n greater than or equal to all set of all such that g of n that exists c greater than 0 and no such that g of n less than or equal to c dot f of n for all n greater than numbers. So here this says that this always defines the least bound. So g of n is always in the least value. That is the best case scenario, which is done by the omega notation. It always defines the minimum time required for the program execution. And the next one is the theta notation, which is an average case. This notation describes the upper bound and the lower bound of an algorithm. So we can define it says that it defines always the exact asymptotic behavior of an algorithm, because we cannot say that the algorithm always works in the worst case or it works in the best case. In reality, any algorithm always works in the average case algorithm. So this theta notation defines the real-time scenario of any execution of an algorithm. So mathematically, this is defined as theta of f of n is equal to set of all g of n if and only if g of n is equal to big O of f of n and g of n is equal to theta of f of n for all n greater than n0. Actually, what does it mean is there exists n complexity which is f of n, which is defined by g of n in such a way that this g of n is equal to big O and g of n is equal to theta of f of n, means this is the average between the worst case as well as the best case. So this is always the average case. The average running time lies between best and the worst and can be represented by the theta notation. It always gives the average time required for the program execution. So these are all the three ways the algorithm execution can be defined as big O, big theta and big omega notations. So pictorially we can give all the asymptotic notation as here. Asymptotic notations are languages that allow us to analyze an algorithm's running time. So how the algorithms execute, how much time the algorithm takes to execute. So this is the scenario which shows the asymptotic notation where we have worst case, best case as well as the average case. By identifying its behavior as the input size for the algorithm increases. So as the size of the algorithm increases, the behavior of the algorithm also increases. That means the algorithm's behavior is defined by the size of the input. This is also known as an algorithm's growth rate. So we can see here, this is the normal curve which is the f of n. So this is the curves with all the things. This is the f of n cases. Now in the worst case, here it is the maximum g of n. Best case, it goes in an average, and now in the average case, this is the average case where it is between the worst case as well as the best case. So this is how the algorithm's behavior and its complexity is represented using the big O, omega and theta notations. Hope it is easy to follow, and thanks for watching.